All right, hello everyone, and welcome to the last talk of this wonderful conference. Speaking of wonderful, before our last speaker, since this is the last talk, I would like to convey my profound thanks to the organizers who did a really wonderful job under unusual circumstances at the last minute to possibly change locations to make it online. The Zulip has been great. The organizations of talks with a historical overview and the interview with Sarah. Wow, what an amazing experience for all of us. So let's give them a round of applause. Thanks, you guys. You constantly are raising the bar for the rest of us that have to organize too. So maybe not. So thanks for that. All right, our last speaker is Isabel Vogt, and she'll tell us about abelian varieties isogenous to a power of an elliptic curve.
Thanks. Okay, so it's really great to be here. What an honor. And so I'm excited to tell you about this paper that I wrote, which the organizers asked me to talk about. So that will come in the second half. But I want to start with more accurately what this title represents. So fix an elliptic curve E over some field K. And as the title says, we want to understand abelian varieties that are isogenous to a power of E. So our goal is to understand the category of abelian varieties over our field K that are isogenous to e to the r for some r. Okay, so if we're in the context of this conference and K is a finite field, FQ, then this is specifying that the characteristic polynomial of Frobenius of such an abelian variety is a power of the characteristic polynomial of Frobenius of our elliptic curve. So you might ask, why is this my goal? Why is this what I want to do? And hopefully I'm going late enough in the conference that this has already been sufficiently answered by many other people who have talked about related things. So I'll just say briefly, perhaps you want to enumerate isomorphism classes of abelian varieties over FQ in an isogeny class. And then you have to ask sort of what sort of isogeny classes might you care about, and you might care about maximal or minimal abelian varieties, in which case you care about abelian varieties that are isogenous to a power of a supersingular elliptic curve. So I think we can agree that this is a category that we'd like to understand. And I've left a lot of blank space because we want to understand this category using some linear algebraic data. More precisely, if we let R be the endomorphism ring of our elliptic curve, and I'm emphasizing that it's endomorphisms as an abelian variety defined over K, that's that little K subscript is going to become important later, then the linear algebraic data that we're going to use to understand this is finitely presented torsion-free left R modules. So really the goal of this talk is to be able to do things like algebra, but with abelian varieties. So we have this category where we have geometric objects, we have morphisms of these geometric objects, but we really just want to do algebra because that's easier. And the reason why we could hope to understand this category using linear algebraic data is that there are some nice functors. So in this direction, Hom, well, this is notation, this fancy Hom R into E. We'll talk about what this means. And then there's more clearly a functor in the other direction, which is just Hom as abelian varieties over K into E. So because E has endomorphisms by R, post-composition with one of those endomorphisms defines a left R module structure on Hom into E. And well, these functors are contravariant, so let's just write the opposite category so that we remember that all the maps are switched, all the orders. Okay, so a little bit more about this functor, Hom R into E. So let's leave it there so you can see it. So this functor, fancy Hom R into E, it appears in papers of Guiraud and Waterhouse, and it's attributed to Serre and Tate. Today, I'm going to follow a presentation in a recent paper of many authors, Jordan, Keaton, Poonen, Rains, Shepard-Barron, and Tate, and that's a lot of authors to write every time I want to refer to them. So when I refer to results in this paper, I'm just going to write JKPRSBT and let you fill in the remaining letters. All right. So if we have, and results I'm going to talk about are related to many other results that are in the literature. Most notably work of Kani, and for non-ordinary abelian varieties, this functor is very related to a functor that's implicit in the work of Sentileghe-Stix that was mentioned in Stefano's talk earlier. Okay, so if you see this this goal that we have for ourselves, understand this category using linear algebraic data, it's very natural to ask what sort of data is captured by this functor, what's captured by linear algebra. So our main question is going to be what is captured about this category that we care about, so abelian varieties isogenous to e to the r, by Hom R into E. And to answer this question, I first have to tell you what this functor is. So let me start with that. So definition of Hom R into E. So again, for what I'm going to be talking about today, we're always going to let R be the full endomorphism ring of E defined over K. Actually, for what I'm about to say in the definition, you just need that R admits a map to the endomorphisms of E, but that's the theorems aren't going to hold unless you have this result. So let's assume that. And it's actually defined on a slightly larger category, so where we get rid of the torsion-free hypothesis. So it's defined on the category of finitely presented left R modules up. And this is our functor, Hom R into E. And now if I don't have that torsion-free hypothesis, I don't necessarily get an abelian variety, but definition, the first show that commutative proper K group scheme. So if I start with a module M, I have to tell you, well, I'm going to call it A, is this commutative proper K group scheme, which is going to be Hom R M E. All right, this is what I have to tell you what it is. I'm going to describe the scheme for you. And to describe the scheme, I'm going to describe what the functor of points is. So I'm going to describe the functor of points and then tell you that this functor, show you why this functor of points is in fact represented by a group scheme. So what's the functor of points? Well, let's let T be a K scheme. So then I'm going to want to know what are the T points of A. So HOM from T to A, we want A to represent the functor where this is, okay, so let's think for a second. It's built out of R modules. So if I have this scheme T, how do I get an R module out of that? Well, I can take HOM of K schemes of T into E. And then, as I said before, post-composition with endomorphisms of E gives you a left R module structure on this. And now I have an R module, so now I can use this R module I already have and just take HOM of R modules of M into this. So this is what we want the functor of points to be. So now I have to show you that this is actually representable. Okay, so now the actual construction of A. So we're starting over here with an R module M, which by hypothesis is finitely presented. So let's use that fact. So pick some presentation of M. So I choose some generators, that's some R to the N, and then some relations, R to the M, and I get this presentation as an R module. And this is just linear algebraic data. So this is given by multiplication by a matrix X on the right. If I think about R to the M and R to the N as row vectors, so this is some M by N matrix with entries in R, giving me this presentation. But remember what R is. It's the endomorphism ring of E. So I can also act on powers of E using this matrix. So I can also take E to the N to E to the M, and I can act by this matrix on the left, and that defines a morphism from E to the N to E to the M. And because the category of commutative proper group schemes over a field is an abelian category, there is a kernel in this category, and I claim that the kernel is a commutative proper group scheme that's going to represent this functor of points that I want it to be. So that's the claim, and let's see why that's true. So the first thing, well, I want to understand the T points of A, so why don't I HOM T into this sequence? So first thing I can do is I can take HOM of T, into this sequence. So this is left exact, so I get HOM T into A, HOM T into E to the N, HOM T into E to the M, multiplication by X. And then on the other hand, I can take this sequence up here and I can take HOM as R modules of this into HOM of T E. This is what I'm going for the functor of points to be. And what I will get is, so all the arrows reverse. So I get 0 to, let me line this up. I get 0 to HOM R of M into HOM TE to HOM TE to the N. And again, my matrix X is inducing this map to HOM TE to the M. And these are isomorphic, and these are isomorphic, and my maps are both induced by this matrix X, and so I get this isomorphism that I want over here. And everything here is functorial in T, so invoking Yoneda's lemma, I'm going to get this functor that I want. So this is the construction of this functor. It's purely formal. It's something about abelian categories that allows you to make this work. Okay, so that was the construction. So now let's state some nice properties of this functor. And these all appear in this paper that I said I was going to follow by JKPRSBT. Okay, so zeroth nice property is that this functor that I've defined for you, this fancy hom of an R module into E, is exact, which is great for our goal of being able to do geometry by just doing algebra, because we can take exact sequences of modules and then we can get exact sequences of commutative proper group schemes. So that's nice. As you might guess, you can determine what the dimension of the image. So I'm going to let, again, A be this fancy hom of R modules of M into E. So if we can compute the dimension of A, and it's simply the rank of M as an R module. Again, this seems good for our goal of doing algebra to get geometry. 2, so now this is something that I said earlier when I said this functor was going to help us understand the category of abelian varieties. So if M is torsion-free, then this A is in fact an abelian variety. And moreover, once you know it's an abelian variety, it's one that's isogenous to E to the R. So, so it does in fact give us information about the category that we cared about. Okay, furthermore, we can say a little bit about what sort of things we get for certain nice torsion-free R modules. So if I in R is a non-zero ideal, then this fancy hom of R mod I into E is isomorphic to this kernel group scheme, E bracket I, which just means the intersection over elements of this ideal of the kernel of that element. And on the other hand, if I take hom R IE, well, you can see this by what I claimed about exactness. This is E mod this kernel subgroup scheme, EI. So if you know something about torsion-free modules over these rings, which are endomorphism rings of elliptic curves, then you see why this third point is relevant. So this is relevant because for R, the endomorphisms of E, every torsion-free R module is isomorphic to a direct sum of ideals. So the category that we had, let me just scroll back up to the very top. Sorry for making you dizzy. The category that we had of finitely presented torsion-free left R modules, it's really easy to understand, right? We have just things that are isomorphic to direct sums of ideals. And so we can push those over by this functor, and we get certain, well, elliptic curves, things that are isomorphic to products of elliptic curves. All right. So that was that. Yeah, let's now do this restriction. So let's now restrict to torsion-free R modules. So now what I'm going to say, this fourth nice thing is only true about this functor when I restrict to this smaller category where I assume my R module is torsion-free. So then in that case, hom R into E is fully faithful. So again, that backs up our ability to do algebra to get geometry, right? So the morphisms as two things in the image, the morphisms as K group schemes are just the morphisms of R modules. With image, well, I already sort of said this, if you combine 2 and 3, and this point I wrote in purple, the image is products of elliptic curves, so the essential image, products of elliptic curves, HOM R I E, and this other functor that I wrote down, this sort of more standard thing, HOM as an R module into E, is an inverse on this image. Can't spell. Is an inverse on this image. So yeah, I think I have enough time to just quickly show you why this is true, just to hammer home the algebra that's going on here. And it's just going to follow from this fully faithful property that we have. So why is this true? Well, what do we have to do to show this? We have to show that if we take HOM of this fancy HOM of a module into E, then at the end of the day, we just get the module back, right? So I'm going to rewrite this as HOM of this fancy HOM of M into E, and then I can rewrite E as fancy HOM of R into E, right? That's clear from the construction that E is in the image and in this particular way. And now I use the fact that it's fully faithful and rewrite this as HOM of R modules. And remember, the arrows get swapped, the order. So this is of R into M, and you see that is, of course, M as we hoped. So so it is just some really sort of basic algebra once you get these results about how these functors behave. Okay, so I think when you see all of this, it really begs the question, what is the essential image? Like, how much of the category we care about does this functor see, given that it's so nice on what we do see? So, question, when are this HOM R into E and HOM into E inverse equivalences of categories? So this is really the question that's taken up in that many author paper that I cited earlier. And I can't get into everything that they do, but let me just say briefly the idea of what they do. So this category, right, it's all abelian varieties that are isogenous to a power of an elliptic curve. So what you have to consider are what are all of the possible subgroup schemes of powers of an elliptic curve that could be the kernel of those isogenies. And if all of those subgroup schemes sort of appear out of this construction, out of this module construction, then you're good. So they make a definition of a subgroup scheme of E to the R being a kernel subgroup. And this is equivalent to it coming from some appropriate ideal in the way that it comes via this module construction. And then what they do is they find necessary and sufficient conditions for all subgroup schemes of E to the R, for all R, to be these kernel subgroups in order, to be seen by this module construction. So I can't state everything. Let me just focus on the case that is of interest in this conference. So K is a finite field. Write it Q. And let's write pi E for the Q power Frobenius endomorphism of E. So then the theorem by these many authors, JKPRSBT, is in the case that K is FQ, in this case, HOM R into E is an equivalence if and only if, one, the elliptic curve E is ordinary, and if I take Z adjoin pi E, which of course has to sit inside the full endomorphism ring of the elliptic curve, if this is actually an equality, it's equal to the endomorphism ring, then this is an equivalence. And if it's ordinary, that's the only way it's an equivalence. And if E is supersingular, and so then there's two possibilities. K is a prime field, FP, and the same condition is true. Z adjoin pi E is equal to the entire endomorphism ring R, or K is FP squared, and R is rank 4. So these are the only possibilities. This is exactly when this gives you an equivalence of categories, and all of these modules can tell you everything you want to know about abelian varieties isogenous to a power of E. Okay, so that was my brief summary of that history. So now let's briefly leave the world of FP. So I can make a few points. Leaving the world of FP, or FQ, let's look at this case that R is again, the endomorphism ring of E is just Z. So in that case, the image of this functor, HOM R into E, well, all of the modules, all of the torsion-free finitely presented R modules are just Z to the R. And we know where Z goes, it goes to E. Z to the R just goes to an abelian variety isomorphic to E to the R. So the image of this is just powers of our elliptic curve, E. But E can be isogenous to a non-isomorphic curve. So, so it looks as though this world of modules can't really tell you something about this case that, or often can't tell you something about this case that that R is just Z. And in fact, a particular case where this must happen, so this must happen if E acquires Cm over a separable quadratic extension K prime over K. So that's what I want to say next. So let's set a little bit of notation. So let O be the endomorphisms of E over this quadratic extension. So by hypothesis, this is a quadratic order. And I'm going to let E prime denote the K prime over K quadratic twist of E. So this is another elliptic curve that's defined over K. It's an elliptic curve over K. And it's not isomorphic to E. It's a non-trivial quadratic twist. But when I base change to K prime, it is isomorphic to E. So I have an isomorphism that's defined over K prime. And let me call this isomorphism phi. So then this fact that this is really a non-trivial quadratic twist says that if I let sigma in the Galois group of k prime over k be the non-trivial element, then if I act by sigma on this isomorphism defined over k, then I don't get back sigma, I get back minus sigma. Okay, so not isomorphic to E over K. However, we have this assumption that over K prime, I have complex multiplication. And so I can choose an element alpha in this order O that's purely imaginary, which means that if I act by sigma on alpha, I get minus alpha. And alpha now defines for me an isogeny of ek prime to ek prime. And maybe you can see where this is going because Galois acts on alpha and on phi in the same way, right? And so if I take phi composed with alpha and I act by sigma, then this is phi composed with alpha. And so this descends to an isogeny from E to E prime defined over K. And so just to scroll up to remind you of why I was doing this, what we found is a non-isomorphic curve, namely the quadratic twist, that was isogenous to E. It was just forced to be there. And it's not seen by this fancy Hom functor, right? Because we only see the powers of E. But that doesn't mean that it's invisible to the world of modules. And so this is my contribution to this topic is I'll show you that there is a way you can still see these sorts of things using modules. And more generally, analogously to how I started the very beginning of the talk, if I have any Galois extension, k prime over k, we can ask, can we understand the category of now abelian varieties over k that are k prime isogenous to e to the r for some r. So I'm requiring that my abelian variety is defined over k, but I'm not requiring that the isogeny be defined over k. That can be defined over some extension. And again, the name of the game is we want to understand this via some linear algebraic data. So let's think about what linear algebraic data we might want. Well, because abelian varieties are projective, I can use Galois descent, and equivalently to specifying an abelian variety over k, I can specify an abelian variety over k prime equipped with descent data for k prime over k. So part of my linear algebraic data is going to be R, which is now the endomorphism ring of E base change to k prime. So I just want to highlight that R has now is the endomorphisms over k prime. And if I let G be the Galois group of this extension, k prime over k, then G acts on R, and I'm going to write this action as R maps to upper sigma R. So this descent data for k prime over k is like giving a G action on everything so that all of the maps are equivariant for that G action. So I think thinking about it that way, it's not very surprising that a pretty good guess for the linear algebraic data would be finitely presented torsion-free R modules with a semi-linear G action. And we can actually make this a little bit more we can phrase this in a different way. So this is the same thing as modules over the twisted group ring. So I'm going to write that as R angle bracket G. So this is, well, it's indexed by elements of the group G. So copy of R for each one of these elements. And then I have the, so here I've written it, suggestively with R on the right. So if I, with sigma on the right, so if I have an element of G on the left, I have to know how to commute it across the element of R. So that relation is tau times R is, well, I have to act on R as I move it across to the other side. So that's what this twisted group ring is. And right, so I can rephrase this as R angle bracket G modules. And the thing that I constructed in this paper, so I'm going to state it as a theorem with then a bunch of nice properties which go as part of this theorem. So there exists a functor, fancy Hom, R angle bracket G into EK prime, which goes from the category of finitely presented left R angle bracket G modules to the category of commutative proper K group schemes, same as before. And let me describe for you its functor of points. So if I have a module here, and I send this to A, which is this fancy Hom R angle bracket G, M EK prime. So I have to tell you what the T points of A are. So Hom of T into A is, again, I'm going to use Hom of R angle bracket G modules, and I can get one by taking Hom of TK prime into EK prime. So I base change to K prime. This now is an R angle bracket G module, and then I can take Hom of M into this. So this is sort of the natural extension of what you want the functor of points to be, given what I said before. So let me state the nice properties now. So this is nice properties / what you need to show this is actually representable by a commutative proper K group scheme. So let's see, nice properties. So the 0th nice property, this is going to be like what you need to construct this. So let's think about mimicking the sort of general abelian category theoretic argument that I outlined at the beginning. So we choose some presentation of our module, some finite presentation, R angle bracket G to the N, R angle bracket G to the M. Again, this is given by some matrix X. And what we want to do is we want to have some objects, Hom R angle bracket G from R angle bracket G into EK prime to the N, Hom R angle bracket G, R angle bracket G, EK prime to the M, where I can multiply by my matrix on the other side and get a homomorphism of commutative proper group schemes, and then invoke the fact that this category is abelian and get the kernel, and the kernel will be my A that I want. So really, in order to construct this, what I need to tell you where R angle bracket G itself should go. That is the key thing. So let's try to think about what should these be. Okay, well, let's look at the functor of points. I told you what I want the functor of points to be, so let's try to look at that and see if we can identify what this variety should be. So looking at the functor of points, so Hom from T into this Hom R angle bracket G, R angle bracket G, EK prime. So this is just what the T point should be. Well, I said this should be Hom of R angle bracket G modules of my module, which is just R angle bracket G itself, into Hom. Now I base change to K prime, EK prime. Well, if these are Hom of R angle bracket G modules of R angle bracket G itself, this is just Hom TK prime, EK prime. So if this were an in-person talk, I would then ask the audience, what is this commutative proper group scheme that should represent this functor, but this never works well on Zoom. So let me just say, I think we could all work out and agree that this is the Weil restriction of scalars of EK prime down to, from K prime down to K. So this is the real thing that you need to work out to, and then it's just some sort of formal category theoretic arguments to construct the functor. So this zeroth nice thing, I see I should have left a little bit more space. This zeroth nice thing is that if I take R angle bracket G itself into EK prime, this is the Weil restriction from K prime down to K of EK prime. And more generally, that's approximately correct. More generally, restriction of scalars, this is a nice geometric operation, right? So this corresponds to taking an abelian variety over K prime and replacing it by restriction of scalars, K prime down to K of A. What does this correspond to on the algebra side? On the algebra side, this corresponds to taking an R module and tensering it up with R angle bracket G. You can also ask for a similar thing, which is what is the algebra analog of base change? So this is taking an abelian variety over K and replacing it with its base change to K prime. And on the algebra side, this corresponds to viewing an R angle bracket G module as an R module. So this second point here is actually very nice, is that this fancy Hom R angle bracket G into EK prime is compatible with the previous functor that I had. So sorry, fancy Hom R into EK prime. When I use two forgetful functors, I forget the G action on the module side, and I base change to K prime on the variety side. So it's compatible with this previous functor, which means any property that you can check under base change, for instance, are you an abelian variety or not, you can deduce from this previous work. So there's a lot of things that you get sort of for free out of this compatibility. Okay, I'm almost out of time. Let me use my last few minutes to just scroll back up here and say, so this functor that I just told you about, it goes in this direction, R angle bracket G into EK prime. So we get abelian varieties over K, and we know what their K prime isogeny class is. So you might ask, what is their K isogeny class? So that's this last nice thing. So if you want to determine the K isogeny class, so let's let F be R tensor Q, the endomorphism algebra. Then in all the cases, I mean, for what R could be as the endomorphism ring of an elliptic curve, F is semi-simple, and it's not hard to show that this twisted group ring is also semi-simple. which means modules over it split as a direct sum of some simple modules. So write S1 through SL for the simple modules. Then there's an analogous functor. Fancy Hom F angle bracket G into EK prime. But the difference is that this is valued in the isogeny category. So the isomorphism class of something in the image here determines the isogeny class. So this is, looking at this, we can figure out what the isogeny class is, and because this is semi-simple, what this says is that the isogeny class, the K isogeny class of something in the image of this R angle bracket G functor is determined by these Hom F angle bracket G SI into EK prime. So it's really determined by this sort of representation theoretic, irreducible representation, these simple objects. So it's very representation theoretic. Okay, so let me do one little example of this to tie back into something I said earlier. So let's do an example that K prime over K is a separable quadratic extension. And again, G is always going to denote the Galois group of K prime over K, which has non-trivial element sigma. So then you can work out the simple F angle bracket G modules are, well, F itself, and this has a Galois action I'm going to write as sigma of X is this little upper sigma X. And then I can twist the Galois action. So I can have this F twisted by sigma, or twisted Galois action. So now sigma acting on X is minus sigma X. So these are the two simple modules, and I think you can probably guess where these, what these correspond to. This F itself corresponds to E, and this twisted version corresponds to the quadratic twist, K prime over K, quadratic twist. So in particular, quadratic twists are always in the image of this functor, no matter what. They're always accessible by modules. And furthermore, if we're in the situation that I highlighted earlier, that F is a CM field, so if F has a totally imaginary element, then these are isomorphic. F and F sigma are isomorphic by multiplication by that totally imaginary element. And so what that tells you is that E and E sigma must be isomorphic in the isogeny category. In other words, they're isogenous. So that's another way that you can see that isogeny that I said at the very beginning. Okay, so let me stop there.
Thanks, Isabel. You're awesome. Do we have some questions for the speaker? Yes, Stefano.
Hi, Isabel. Thank you very much for the talk. So I have a question about the modules. Is there a classification, a structure theorem of these R bracket G modules? Are all direct sum of some nice stuff? Or?
Yeah, I don't know. I don't know of one. I mean, you might hypothetically have to do like lots of different finite groups. So yeah, it's a good question to try to understand what the essential image of this is. The reason I got into this was actually because I wanted to do something just with quadratic extensions where I worked out the examples that were important to me. But it's a good question. Yeah, I don't know off the top of my head.
Thank you.
Thanks for that question.
Can you replace E by a simple abelian variety?
You can do that.
No, but I meant how much of formalism
Okay,
you
so
get to work.
yeah, so it's a lot harder. So in this, so you can define this functor. I mean, it makes sense for something that's not an elliptic curve, for sure. Let me go up to this theorem. These many authors give a partial answer using the functor that Stefano talked about for non-ordinary abelian varieties over prime fields. They give a partial answer for higher dimensional abelian varieties, which again says that the condition is like I wrote it here, that, that if you take z adjoin pi, then you get the endomorphism ring. So that is some partial work in the case of prime fields, but yeah, in general, it can be an equivalence of categories and it can not be.
Thank you.
Thank you. Drew, do you have a question?
Yeah, I was actually going to ask a special case of what Armand just asked, which is what if E is replaced with a QM abelian surface or a CM abelian surface? Those seem like the places where it might work.
Yeah, it's a good question. I haven't thought through what goes through, but I think it's definitely a good question. Open problems for everyone to think about going forward.
Maybe Stefano is going to help me also remind me, what's the title of this paper where someone, does something about replacing E by an abelian variety of higher dimension?
So there is something in this long paper by all these authors. It's called what my title of my talk is, Abelian varieties isogenous to a power of an elliptic curve.
Yeah, but I'm thinking about another one. There is another paper, and at some point with Stefano, we had a discussion because we were trying to understand if it would apply or not, but I forgot the name now. I was wondering if Stefano would remember. Yeah, Amir Khosravi. Yeah. Thanks, Valentine. You have a better memory than me. And in these papers, it seems that there is something to say about this, but it's not very clear to me what it means. But I had also a question for you, Isabel. Is that, and did you try to understand what happens to the polarization in this context?
No, I didn't, but it's a good question because, in this prime field case, this functor really does agree with that Stix functor. They prove that. So given recent work about polarizations there, I think it's an interesting thing to ask for sure.
I love the idea of a hive mind where we can all recall each other's brains for where papers were. That we're going to get an amazing amount of work done. I have a question for you, Isabel. I hope it's within the scope. It's on the slide that you're on right now. What's the probability? R is the endomorphism ring of E, I think. What's the probability that that endomorphism ring is generated by Frobenius? So your condition one says, you get an equivalence if this thing's hold. Is it all the time? Is it most of the time?
No, it's definitely not all the time. So
well, I mean 100% of the time or something.
Oh, you're asking like a statistics question. Well, so if you look at this paper, I'm going to answer this one because I remember it worked out in this paper. They work out what the characteristic polynomials of Frobenius are for these supersingular elliptic curves over prime fields, and they show that in all but one case, I believe, there's one possibility for what it looks like when it's not equal to R, and in the other cases it's equal. Does that answer your question?
I think so. I mean, it's not fair to, I'm glad you'd answered in the quaternion case, because of course that's the one closer to my heart, but okay. Maybe for this audience, it's more relevant to ask this in the ordinary case, because there must be some question about if it's a maximal order or not, and what's the probability of an isogeny. And it feels like there's a little statistics or analytic number theory question.
Right. If it's a maximal, if z adjoin pi is a maximal order, you're done. You're good. Right.
Exactly. And does that happen most of the time? I feel like.
Francesc says in chat that Alina Kojikaru has maybe investigated this type of question.
Cool.
I would think it happens not 100% of the time, but just a positive fraction of the time, just the same way that square-free integers are a positive fraction of integers.
Yeah, I mean, if trace squared minus 4 times p is square free, then you're in. So already that counts for a positive fraction.
Yeah.
Great, thanks. Do we have any other questions for Isabel? All right, let's give her another round of applause. All right, I guess I'll turn it back to the organizers in case they have any concluding remarks.
Okay, so maybe I can just make some small remarks at the very end. So first of all, thanks all of you for coming and attending and being so active. It was really nice to see how much activity there was on Zulip and during the talks. I was really very happy to see that there is such a big interest, also that the community is very vibrant and so many open questions, interesting remarks and so on. So, I mean, the aim of the conference was to kind of give a rough overview of what has happened after the 1985 lectures of Serre, to talk about kind of what is current research interested in and make some guesses about the future. And that's, of course, a very difficult task, but I think all of our speakers did a marvelous job. So I would like to thank all of them on behalf of everyone for their great talks and their contributions. And their work is not over. So they had also agreed to write up what they had talked about. So hopefully in some time we will have some kind of printed version of all of these talks, maybe expanded. And I'm sure that all the discussion on Zulip and during the talks will really feed into it. So that's also a point where I would like to thank everyone to really participating so actively. And I mean, we're really surprised to have more than 300 people registered, and each of the talks more than 50 people following. So about Zulip, it will be on for some more time, and the videos have been recorded. You can find the links in the Zulip chats. What will happen with them, we'll have to see, also talking to the speakers and so on, but we'll announce it on Zulip what will happen to the videos that have been recorded and the slides, so you can follow from Zulip what will go on. Finally, I'd like to thank the Foundation Compositio Mathematica for their support, the University Neuchâtel for their help during the interview with Serre, and Bozic University for their support for the technical infrastructure, and of course all of you for coming, and hope to see you all soon again somewhere.
Thanks to all of you, and if I can say, have a safe trip back home.
Yeah.
Bye-bye.
Thank you. Bye.